PC 111 lecture 14, set 3. We're going to continue talking about the final project and the optimizations that can be done for the final project. So here, I have an interface for this final project module, which looks very much similar to the interface you have seen in the earlier assignment. Here, of course, the difference is the yellow module that I'm putting here, which is a Bitcoin hashing, which is specific to this project. And, what it does is kind of the interface is similar, but, in this case, we are going to read 19-word block header starting at the address block header. We are going to compute the final hash for 16 nonces. And so each message, that we are going to have is like a block header and nonce. And then we just write the final H0 for each of the 16 nonces into the memory, starting at the output address. And then when done, we're going to set this done to 1. And, we are going to be done with the whole computation. But like the interfaces of this, you're going to write the controller that does this, and it's going to read and write these values and do the computations for Bitcoin hashing. But the interface to the memory and kind of the input output is what you should be familiar with, because this is something that you will see if you get to write Verilog programs. This is something that you will get to see a lot in practice. Now, the final hash value, as we mentioned, is going to be in H00 to H015 in 16 words to the memory starting at the output address. And, there are 2 blocks for each input message. There are 8-word hash value created for each block. So because we have two of these, we will have 8 words of hash times 2 times 16 words for the hash to be stored in the memory. And, here the assignment is to design the yellow box, assuming the port names and module names that are given here. So this is to simplify your job. We will have the module Bitcoin hash, the yellow module, which takes as the input, the clock, the reset, the start, and then, oops. Let me just move this up. The message address. So basically, we have the message address, we have the start, we have the output address, and then we have the reset and the clock. Now, the output, is going to be kind of when we are done, we are going to have the logic done. We are going to, we have this output to memory clock, memory address, memory write enable, the memory write data, and we already mentioned the memory read data as an input, which is here. So whatever you see in this picture, you're going to directly translate it into this figure. So the basic implementation, if you just did this as we mentioned, takes at least 2,147 cycles. And this is because, we're going to read the 19 words, which is going to take 19 cycles. And then we're going to output every time, we have for each nonce computation, we're going to output it. So that's another 16. And in the middle, as you remember, we did 164, one round of hash for the first 16 words, which is 64 cycles. Then, for the hash of the rest, for the second block of the first SHA-256 hash, we had the, we had 16 times 64, which is 1000 times 24. For the second one, the same. We have 16 times 64, which is 1024. And so the for making this possible for all the nonces, we have at least 2,147 cycles. Now, if we hide the reading kind of part, which means that, we hide this reading of 19 words and we kind of think that we already have them as, on the fly. So, we just, kind of think that, this is the same for all 16 nonces. Then, we could lower this by a little bit to 2,128, which which is slightly smaller. But we, in order to do this efficiently, we need to do these in parallel. And one way, I mean, in the project, we are going to first do this sequentially. But of course, if you want to get like less time and do more efficient implementation, and that's actually what happens in practice. Remember, the Bitcoin miners, they need to optimize for time, because that's how they make money. If they do things sequentially, they're not going to make money. And usually the state of the art is that they try to make ASIC chips that are basically having this amazing parallelism inherently inside them. And with that amazing parallelism, they're going to run and they're going to, do the computations. Now, if we want to do this, on 16 parallel inputs. So we are going to create 16 set of registers that are input registers, 16 set of logic for the SHA operation for the same state machine control. And now, this is, of course, by no means the only implementation you could have. You could kind of also use other ways to implement parallelism. The important point here is that we do not want to talk about, we do not want to do parallelism but have multiple state machines. You want to have the same state machine that implements parallelism and has control over all the nonces. So that is something that you could do in other ways. Another way to do it is to have, in instantiation of the SHA-256 module. So every time, there is this there is this variable that we have discussed in the syntax of the Verilog, which is a genvar. And what genvar does is that it has the ability to generate more hardware in parallel. And so what it does is that, this is typically the genvar has to be described outside the always flip-flop. And what happens is that it's going to, every time we have we have this parameter, every time we have a new value for this parameter, which is in the for loop specified here. Say in our project we have 16, so it's going to generate 16 copies of this. It's going to generate this block. And then, this is basically the standard interface for this block that we have had from before. And every time, once we end generation of these, then what happens is that we're going to talk about the states passed to each of these different generated blocks and computing them in parallel and getting the results back. And, for the final project, again, we have the sequential version, which minimizes and we want to minimize the area delay product for the sequential version, which will be, there is an optional part, which, I hope, can be done by many of the groups, where a parallel version we are doing to minimize delay only, because delay, as you remember, has been the most important constraint that people who are doing Bitcoin mining are realizing. So I'm going to discuss in the next set some hints and expected range of results.